Hello everyone. In this video we'll do one more practice proof using predicate derivation inference rules. This one will help us use universal elimination and universal introduction together. It's a short little proof, and this one's a theorem. It says for all x, if for all z, lxz, then lxx. It basically says everybody who loves everybody loves themselves. And as usual, we're gonna do some goal assessment. The good thing to do with theorems, because you only have a target sentence, you don't have any primary assumptions in a theorem. So go ahead and hit pause on this video, take a look at that target sentence, and come up with an idea or two about strategies for bringing the proof to that target sentence. What would be some of the last or next to the last steps you think you should take? So go ahead and hit pause and resume the video when you're ready. Okay, if you look at the target sentence, you notice that it's a universally quantified conditional sentence. And there's two big clues in terms of how we might strategize to get to this sentence. The last step, you might think, would be an application of universal introduction, because it is a universal generalization. And that means that the last step is going to have to be an instance of that universal generalization. So let's write down an instance. For all z, L, A, Z, horseshoe, L, A, A. Okay? So that is as an instance of this generalization. It's a conditional. And in place of all of these x's we see here in the target sentence, we have the name A. It won't matter at all what name you choose. I tend to go in alphabetical order from the beginning of the alphabet. But you can choose a different name if you like. So this this conditional says simply, if the individual A loves everybody, then A loves A. That's a conditional sentence, and if you remember your sentence logic derivation rules, you know that the rule conditional introduction is a pretty good way to prove conditionals. Okay? So we also know from sentence logic that conditional introduction is a subderivation rule. So we need to insert into our derivation a scope line. And that's in fact going to start the derivation. So if we start with subderivation just like that, the rule conditional introduction tells us that we have to have a subderivation that begins with the antecedent of the conditional that we want. For all z, L, A, Z, that's an assumption for conditional introduction. And then the last line of the subderivation is going to be L, A, A. If we can put together this kind of a subderivation, that gives us the conditional by conditional introduction. And if we can get this conditional, then we can apply universal introduction to it. So here's a quick question. How can you get from line 1, for all z, LAZ, to this new target, LAA? You might want to hit pause in the video real quick, come up with some idea, and then resume when you're ready to move on. Turns out that the step from the universal generalization on line 1 to the last line of the subderivation is actually just one quick step. It's an application of the rule universal elimination on line 1. Universal elimination is an easy rule to apply. It has no restrictions. Simply tells you to drop the quantifier and replace the variable of quantification with any name. So we drop the quantifier, we would get LAZ. If we replace the name, the variable z, with the name A, then we get LAA. So this proof is already figured out from there on. Line 3 is an application of conditional elimination on lines 1 through 2. That was the extent of the subderivation. And then line 4 is an application of universal introduction on line 3. I do want to make one comment. The name A in line 3, which we are replacing with variables in line 4 and adding a universal quantifier, that name A appears in an assumption, doesn't it? And we know that universal introduction has some restrictions on it. The name A cannot appear in the result of the rule application, and we took care of that by replacing all occurrences of A with X. Okay. The other proviso or restriction on universal introduction says that the name A cannot appear in any live assumptions. Does this name appear in any live assumptions? The answer is no, it doesn't. The name A does appear in an assumption up on line 1, but when we're down here on line 3, which we're taking as input for universal introduction, when we're down here on line 3, A no longer appears in a live assumption. That assumption that started on line 1 is discharged, we say, on line 2. So when we're back out along the main scope line on line 3, A is safe for universal introduction. So this is one of those cases where the name A was introduced to the proof not by universal elimination. The name A was introduced in an auxiliary assumption. And that is another way that we can work names into our proofs. When we discharge those assumptions, we end the scope line that the assumption begins. We move to the next outer scope line. Any names that were introduced in that way are usually pretty safe for applying universal introduction to.